Okay, so in other words, I can say that IKL equal to IN 2 pi. So IKL equal to IN 2 pi. So I take out the I, so I get KL equal to N 2 pi. So K equal to N 2 pi over L. Right? This one. So after you resolve it, you get this allowed value of K. So the allowed value of K equal to N 2 pi over L, where N equal to 0, plus minus 1, plus minus 2, and so forth and so on. So this is the allowed value of K. So now we plot this allowed value of K along a K axis. So they form one-dimensional mass of regularly spaced point. So the spacing between the point is 2 pi over L. Why? Because when you substitute n as 1, 2, 3, so the first one will be 2 pi over L, the second one is 2 times 2 pi over L, the third one will be 3 times 2 pi over L. So the difference is 2 pi over L. So the spacing between this point is 2 pi over L. So if the bar length is large, then the spacing becomes small and the point form a quasi-continuous mass. Okay, so the spacing is 2 pi over L, and this 2 pi over L depends on this L. Only the L is the variable. If the L means the length of the bar, right? Just now, if you remember, I told you that this L is the length of the bar. If the L is very, very large, that means that the spacing between the point will become very, very, very small. Okay, the spacing between the point is 2 pi over L. So when L is large, then 2 pi over L will become very, very, very small. Okay, so suppose we choose an arbitrary interval dk in the K space and look for the number of modes whose case is lying in this interval. So we assume here that the L is large because in the real world, the material in the real world is quite large if you compare with the distance between atoms. Okay, in maybe one handful, the dimension is maybe like 10 cm, but the distance between atom and atom is just like 2 angstrom. Okay, so 10 cm is much larger than 2 angstrom. Okay, so we can assume that the L is large, so that the points are quasi-continuous, and then this is true for the macroscopic object lah, because like what I told you just now, in the macroscopic world, in our real world, all the solid are relatively larger or large if compared with the distance between two atoms. So just now remember we have K equal to N 2 pi over L, then N equal to 0, 1, 2, 3, 4 up to infinite. So we plot this in K axis. So we have when n equal to 0, we get 0. When n equal to 1, we get 2 pi over L. When n equal to 2, we get 2 times 2 pi over L. When n equal to 3, 3 times 2 pi over L, and so forth and so on. Okay, so when L is large, then 2 pi over L will become small. Then the point will become closer. Okay, why? Because 2 pi over L is reciprocal. When L large, then this 2 pi over L becomes smaller, so the distance now becomes smaller, although it's still 2 pi over L. Okay, but just because L is large, so the point will become very close together. So each k value or each point represent one quantile mode of vibration. Okay, so for an arbitrary interval dk in the K space, the number of modes will be dk over 2 pi over L equal to pi over 2 L over 2 pi times dk. What I mean? Okay, remember I say that lattice vibration for non-lattice vibration. Okay, so if lattice can only vibrate in one particular omega, okay, and omega has a dispersion relation with k. You remember in the last chapter we find the relationship between omega and k. So omega can actually change k and k can actually change omega. Okay, up to here, okay, right? So now, each lattice point can only vibrate with certain omega and certain k based on the equation that we obtained here. How do we obtain here? We assume that x equal to 0, the state of x equal to 0 is exactly equivalent to the state when x equal to L. And then we solve the equation, and then we got A, blah blah, this one, then we get this one. Okay, I already explained just now. So now we know that these are the allowed k value. Okay, allowed k value. So if you want to know how many mode in one particular range, so the solution is very simple. The number of mode, how many mode in one particular range, the number would be dk over 2 pi over L. Okay, why dk over 2 pi over L? Let's say I want to know how many mode in this region. So I just measure what is the length. Let's say the length is dk. Okay, from this point to this point is dk. So what is the distance between lattice point? 2 pi over L. So when I use dk over 2 pi over L, then I will get the number of mode. In other words, let's say I want to know what is the length of this one. Okay, I know that this length is, let's say, xcm, and then the distance between lattice point and lattice point is 0.5 cm. So if I want to know how many lattice point in this length xcm, so I simply use 8 over 0.5, then I will get 16. Right? So I know that, okay, there are 16 mode. But now, we want to know the number of mode in the frequency range of d omega. Okay, and we know that the number of mode in dk should be same with the number of mode in omega. Why? Because k is correspond to omega by the dispersion relationship. Okay, so the number of mode in frequency range d omega between omega and omega plus d omega is g omega d omega. Okay, so g omega is the density of state, and this number is same as the number given by equation 10.6, this equation, because the number of mode that we obtain based on k, the wave vector, should be equivalent to the number of mode that we obtain based on omega. Okay, because we have the dispersion relation between k and omega. So the density times the length of the omega equal the density times the length of wave vector. Okay, so density times length, we know that definitely we'll get the number, right? So g omega d omega equal to gk dk, and gk dk is what? Is the number of mode. The number of mode we also previously have obtained it through equation 10.6. So we substitute this one with equation 10.6. So we move the 10.6 into here. So we get number of mode by the frequency angular frequency equal to L over 2 pi dk, equation 10.6. So now, based on this equation, when you rearrange it, you'll get g omega